What happened in the first microseconds after the Big Bang? What did matter look like before atoms even existed? Why does the universe exist at all? To answer these fundamental questions, I traveled to CERN in Geneva. Let me know in the comments if you'd like to see more on-site reports like this. I'll try to organize more of these this year. And subscribe to the channel if you don't want to miss it. Welcome, everyone.
Guys, I'm here 60 meters underground at the ALICE experiment at CERN, and here the researchers are trying to do nothing less than recreate the conditions that existed just a few microseconds after the Big Bang. Sounds incredible, and it is. And I have to tell you, this place really feels less like a research center and more like a mix between science fiction and a cathedral. It's totally mind-blowing, and we're going to take a closer look at it now.
The journey to ALICE is an experience in itself. Together with Professor Carsten Welch from the University of Liverpool, I made my way through a labyrinth of corridors and security checkpoints. The security measures here are extreme. After all, we're at one of the most important research centers in the world. We took an industrial elevator 60 meters underground, a ride that felt like a journey through time. Because what awaited me down there is a machine that literally turns back time to the moment when our universe was just a few microseconds old. When the elevator doors opened, I stood before one of the most massive scientific apparatuses I've ever seen, ALICE. That stands for a Large Ion Collider Experiment. It is 26 meters long, 16 meters high, and weighs an incredible 10,000 tons. And the cavern in which it all stands is huge. You could easily fit a multi-story building in here, but what exactly is being researched here? To understand that, I spoke with physicist Kai Schweder, the project leader of ALICE.
What does this experiment do? What do we want to find out there?
So ALICE is one of the 4 major experiments at the Large Hadron Collider. That's the most powerful accelerator in the world. And we are one of the experiments, and we specifically conduct nuclear physics. We collide the heaviest atomic nuclei at nearly the speed of light, and we want to create a type of matter that permeated the entire universe. A very short time after the Big Bang, about a millionth of a second after the Big Bang, the entire universe existed as a soup of elementary particles, quarks, and gluons. And back then, the universe was without structure, and only later did protons and neutrons form the atomic nuclei, the hydrogen atoms, and so on. And only then did the universe gain structure. To this day, there are the largest structures, galaxies, galaxy clusters, and the universe has expanded tremendously since the Big Bang 14 billion years ago.
While most people associate the Large Hadron Collider with the search for new particles like the Higgs boson, ALICE has a very special mission, the study of Quark-Gluon plasma. Quark-Gluon plasma is a state of matter so extreme that it presumably existed only in the first microseconds after the Big Bang. It is the state in which matter is, so to speak, completely melted. Imagine heating normal matter further and further. First it melts, then it vaporizes. But what happens if you keep heating the gas even more? Eventually, all structures dissolve. The protons and neutrons that make up all atomic nuclei disintegrate. All that remains are their fundamental building blocks, quarks and gluons, floating freely in a cosmic primordial soup. To achieve this state, unimaginable conditions are required. Temperatures of about 1 trillion degrees. That's 100,000 times hotter than the center of the sun. And ALICE creates exactly these conditions. But of course, a real CERN physicist can explain this much better.
We want to recreate the conditions shortly after the Big Bang. And as you already mentioned, we want to produce this quark-gluon plasma. And now most viewers are probably wondering, what on earth is quark-gluon plasma? Could you explain that for us again?
Yes, of course. We know what an electron is from chemistry or physics class. That's an elementary particle. Elementary means it has no internal structure. It's not made up of anything. It has no substructure. It's a single particle, and it participates in electromagnetic interactions. We know about currents, magnetic fields. That's all due to the electron. And so if you look at the simplest atom, for example, the hydrogen atom, there's an electron buzzing around on the outside. And if you look inside, there's a proton. And the proton, in turn, is made up of smaller parts. That's not yet an elementary particle, but that's where you find the quarks and the gluons. The quarks, you typically find 3 quarks that make up the proton, and these quarks are held together by the gluons. That's the glue. The English word glue means adhesive. So the gluons hold the quarks together inside the proton, and together these are the elementary particles of the strong interaction, and they've never been observed freely. That's a very special property of the strong interaction. I can obtain a free electron. If I take a hot wire, heat it up, apply an external electric field, then I have a free electron. But the quarks, they are always confined within the proton. No matter how hard we collide particles together. But you can do the following. If you heat up nuclear matter, that is protons and neutrons, extremely, then for a short time they become almost free. That means they can move over distances greater than the size of a proton. And that's exactly what existed in the early universe. Back then, all the matter we know today, you, me, our planet Earth, our sun, all the planets in our solar system, and in fact all the galaxies, were united in a sphere with a diameter of 50 kilometers. And at that time, there were only the elementary particles, electrons, neutrinos, quarks, and gluons. And we want to recreate just a tiny droplet of that state from the early universe.
But how exactly does all this work? The trick is simple, at least in theory. Alice uses the Large Hadron Collider to fire heavy ions, mostly lead nuclei, at each other at nearly the speed of light. And when I say nearly the speed of light, I mean it. The ions are accelerated to 99.999% of the speed of light. These are speeds at which time itself slows down. When these ions collide head-on, a droplet of quark-gluon plasma forms for a tiny moment. We're talking fractions of a nanosecond. The matter becomes so hot that the protons and neutrons literally melt. Their constituents, the quarks and gluons, are released. For this brief moment, matter exists in its most elementary form, just as it must have existed shortly after the Big Bang. But then, almost at the same moment, the plasma cools down again. The quarks and gluons recombine into protons, neutrons, and other particles. A veritable avalanche of particles ensues. A single collision can produce up to 3,000 charged particles that fly off in all directions. And then the real magic begins.
Assuming everything has worked out, we have managed to create quark-gluon plasma. How does Alice even detect that? How do I measure that?
Yes, we've just completed an upgrade. We are recording data at the highest collision rates. That means per second, 2 atomic nuclei, 2 lead nuclei collide 50,000 times per second. And we record every single collision. In fact, we continuously record all detector data. So we don't have a trigger. Everything is written to disk and analyzed. And that's how we reconstruct what comes out of this collision. Subatomic particles come out, which then hit our detector again. These can be electrons, the heavier sisters of the electrons, the muons, those are protons, kaons. So the subatomic particles, their names fill the entire Greek alphabet. And we measure every single track collision by collision. And we also determine what kind of particle comes out. And from that, we want to draw conclusions about what is actually happening in such a collision and whether we have created the quark-gluon plasma. And if we have created it, we want to see what properties it has.
The detector is structured like a giant onion. 18 different layers surround the collision point concentrically. Each of these layers measures different properties of the resulting particles, their trajectory, their velocity, their energy, their charge. Some detectors use the Cherenkov effect, the glow that occurs when particles travel faster than light through a medium. Others measure the transition radiation or the energy loss of the particles. And in addition to the main detector, which measures the entire particle shower, there's also the muon arm.
Yes, we've now walked all the way around here. I think you can really get a sense of just how gigantic everything is here. And now we're behind the big magnet at what's called the million arm. So there's a whole structure behind here made up of several layers because the millions, so to speak, of heavier electrons are very reluctant to interact. And they manage to race out of the main structure all the way to here, while the other particles, which we don't want to examine right now, get stuck back there. That means, practically speaking, only the millions mainly arrive here, and then they are examined here layer by layer.
What makes it all special is the precision with which the particle type can be determined. While other detectors at the LHC mainly search for spectacular new particles, this one is specialized in identifying nearly every single particle produced in the collision. And a few months ago, the physicists discovered something absolutely mind-boggling. They had achieved what alchemists in the Middle Ages had always strived for. They had turned lead into gold.
All the gold owners have already looked at their portfolios in shock. Since then, the gold price has still gone up again, but that's for a different reason. Was it exaggerated in the media, or what exactly happened there?
No, they reflected it very well. We issued a press release. From Alice, we turned lead into gold, and that was picked up strongly by the press. That was actually it had the highest visibility of all results at CERN in the last 10 years. And I think it was very well done. It was reported scientifically in the media, in print media, but it was also seen everywhere on TV. And we turned lead into gold by taking lead and removing 3 protons. If you look at the electron shell, like in chemistry class, nobody knows the periodic table by heart when it comes to the higher numbers. But lead is in the position 82, so it has 82 electrons, and gold has 79 electrons. And if I now remove 3 protons from the lead nucleus, then lead becomes gold. And we did that in special collisions that we detected. And the gold that we created, it's as much as a bacterium. You couldn't see it with the naked eye. So in 10 years, we have produced a millionth of a gram of gold. So nobody's getting rich from this.
But it's still incredible. Fascinating, because I mean, yeah, the statement, we turned lead into gold, it's true in the tiniest amounts, but still.
Exactly. That was the dream of the alchemists in the Middle Ages. Back then, people believed there was a stone. If you had this stone, the philosopher's stone, if you had a stone, if you touched a material as plain as lead, which looks very dull with it, it would turn into gold. And gold is expensive, it shines, it looks amazing. That was the dream of the alchemists in the Middle Ages. Of course, that didn't work. You really have to change things inside the atomic nucleus, then it works. Yes.
They were missing particle accelerators in the Middle Ages.
You might be wondering, why all the effort? Why are we interested in a state of matter that existed for only microseconds after the Big Bang? The answer is because we want to understand how everything came to be from nothing. After the Big Bang, the entire universe was a quark-gluon plasma. As it cooled, the first protons and neutrons formed, and later the first atomic nuclei. Without this transition from plasma to normal matter, there would be no stars, no planets, and no us. But Alice is exploring much more. One major mystery, for example, is the so-called viscosity of the quark-gluon plasma. Is it more viscous like honey or thin like water? Measurements show it is surprisingly thin, one of the least viscous liquids we know of. This has far-reaching consequences for our understanding of the strong nuclear force, one of the 4 fundamental forces of nature. Or take neutron stars, the densest objects in the universe apart from black holes. Inside these stellar corpses, conditions might be as extreme as those in quark-gluon plasma. Perhaps exotic states of matter with strange quarks or so-called hyperons even exist there. All of this helps us answer these questions.
So what is the gain in knowledge if I end up looking at the Quark-Gluon plasma? What can I find out about the early stages of the universe?
For example, I can see what properties it has there, like what temperature. The first thing we want to measure is the temperature. We've already measured that, yes, with the data set from the last 10 years, but with low precision. And if you look at it, the temperature is about 100,000 times hotter than the core of our sun. That means our sun has about 15 million degrees or 13 million degrees Celsius. That means in today's universe, there is nothing even remotely as hot as a quark-gluon plasma. For 14 billion years, the universe has been expanding and cooling down, and there is nothing even close to being as hot as a quark-gluon plasma.
Yes.
We want to see, is the quark-gluon plasma transparent now? Can particles fly through it without being much disturbed? Or is it more opaque, that is murkier? And here too, the heavy quarks are special probes to measure this opacity. I don't really have a good German word for it right now. So temperature and also transport properties. How do heavy particles interact with the quark-gluon plasma?
Now we're back upstairs. We were just 60 meters underground at the Alice detector, and here on the outside wall of the building, you can see a depiction of the detector at its original size. When we came in here earlier, I couldn't believe it. Now that we've been down there, I believe it right away. This is the impressive original size of this thing. It's incredible. And now I'm already completely blown away. But let's see what else we can discover here.
My visit to the Alice detector showed me once again how fascinating basic research is. Here, 60 meters underground, researchers are tackling nothing less than the biggest question in the entire cosmos: what really happened shortly after the Big Bang. But my visit to CERN also took me to another fascinating place, the antimatter factory. And here, they're dedicated to answering an equally colossal question. Why does anything exist at all? Why didn't matter and antimatter annihilate each other? Feel free to click on the video below to watch my report from the antimatter factory. It's truly fascinating. And consider subscribing to the channel if you enjoy these kinds of on-site science reports. Everyone who follows the channel supports my work immensely, and who knows, maybe together we'll get to the bottom of the universe and its secrets.